Okay, so here we've got number one from the packet all the way, from the problems all the way at the back of the packet. It says work and energy practice at the top. Tells us an 8-kilogram box starts from rest at the top of a ramp. The box slides frictionlessly down a 5-meter long ramp, which is sloped. Let's fix that. Which is sloped at an angle of 24 degrees from the horizontal. At the end of the ramp, the box then slides across a horizontal surface where there is a frictional force of 30 newtons acting on the box. In part A, it's asking what is the speed of the box at the bottom of the ramp, and part B is asking how far along the floor will the box slide before coming to rest. And then it gives us the picture. So we've got our ramp, and then we've got the floor. It tells us that just this distance is 5 meters. And there's a frictional force down here equal to 30 newtons. And this angle is 24 degrees. And there's no friction on the ramp itself. Okay, so let's list what we know. We know that the mass is 8 kilograms. We know that the distance it travels down the ramp, I'm going to call that delta x, is 5 meters. We know that the angle is 24 degrees. I'm just calling it 5 since it is an angle of incline. And we know that the frictional force is 30 newtons. And given all of that, we're looking for, I'm just going to call this delta x for the ramp. Given all of that, we are looking for the speed at the bottom, so I'll call that the speed at B. And we're looking for how far the box will slide, I'll call that D, since we will be dealing with work. So on the picture, what's happening, you've got a box starting from rest. It slides, gets to the bottom of the ramp, gets over here, starts slowing down, and then comes to rest again. So we're not given too much in terms of numbers, but if we want to label this a little bit farther, we know that from here to here is my height at A. If I call this A, we can call this B, and we can call this C. So we've got a height at A, we've got our base level. So we know that it starts from rest at A, we know that it's moving at B and it's at the base level, and we know that at C it comes to rest at the base level. Let's draw the energy bar charts. So an A, a B, and a C. And I think in C we're going to need that extra dissipated column. And label this, so we have EEL, EK, EG, EEL, EK, EG, EEL, EK, EG, and my dissipated energy. This is for A, for B, and for C. Okay, so at A, there's no spring, it's not moving, it is above the base level. At B, there's no spring, it is moving, but it's at the base level. And then at C, there's no spring, it's not moving, it's at the base level, so all of the energy is dissipated. Energy at A equals energy at B plus some kind of work, which equals the energy at C. So I could have split this up into two problems, treated part A of the problem separately than part B of the problem, but I'm just going to combine this all together. So I know that my energy at A equals whatever energy is at B. And then I know that my energy at B plus some kind of work equals my energy at C. So that's why the plus work is only right here, because work happens between B and C. For part A, I'm only concerned with energy at A and energy at B, so I'm going to look at that part for right now. So we're looking in part A. So energy at A equals the energy at B. EGA equals EKB. MG, height at A, equals 1/2 m V at B squared. Masses cancel and get rid of the fraction. So 2G, height at A, equals VB squared. Here's my only issue. If we remember from the picture, so you should have that in front of you, we've got this triangle. We knew the distance there was 5 meters. We knew the angle here was 24 degrees. We did not have the height at A. So we have to do a little bit of trig. Given the angle and the hypotenuse, we're looking for the opposite, so I want to use sine. Sine theta equals opposite over hypotenuse. So the hypotenuse times the sine of the angle equals the opposite side. So this is the opposite. 5 meters sine 24 degrees equals that height of A. Making sure your calculators are in degrees and not radians. We get 2.03, keeps on going, meters for the height at A. So 2 times 9.8 meters per second squared times 2.03, keeps on going, meters, equals VB squared. 39.86, keeps on going, meters squared per second squared, equals VB squared. Square root of that, 6.31, keeps on going, meters per second, equals VB. I think we only have one sig fig, so the speed at B is approximately 6 meters per second. So looking from the top of the ramp just to the bottom of the ramp, this is a pure energy problem, conservation of energy with no friction, with no work being done. The only little twist to this problem was the fact that you were not directly given the height at A, you had to use the trig. So now let's look at what part B is asking for. How far along the floor will the box slide before coming to rest? So going back to the bar charts, we're looking between B and C. So the energy at B plus some kind of work gives us the energy at C. And because there is no mechanical energy at C, so there's no elastic potential, gravitational potential, or kinetic, it's all dissipated energy, my energy at C is equal to 0. So the energy at B is equal to negative work. Kinetic energy at B equals negative work, 1/2 m VB squared equals negative FD cosine phi. Again, just getting rid of the 1/2 because I don't like fractions. MVB squared equals negative 2 FD cosine phi. We're looking for D. MVB squared over negative 2 F cosine phi equals D. Okay, we know the mass, we know the speed at B, we just found that in part A. We know that the frictional force causing it to stop is 30 newtons. The only thing we need is the angle. So, work diagram. As the box is sliding, friction acts to the left, box slides to the right, so my angle phi is 180 degrees. So my mass, 8 kilograms, times the V at B, this is the 6.31, again unrounded, meters per second squared, over negative 2 times 30 newtons times the cosine of 180 degrees equals D. The negative will go away because the cosine of 180 is negative 1. So 8 times 6.31 squared over 60 is equal to my distance. This comes out to 5.31, keeps on going, meters for the distance. Again, we only have one sig fig, so the box slides about 5 meters before coming to rest. So once again, this was essentially two problems combined into one, so a conservation of energy and then a problem with work. I chose to make it an A, a B, and a C. You could have looked at part A and part B independently with the only thing connecting them the speed at B, or you could have done it the way I did. Neither way is wrong. I've done it both ways, and you should get the same exact answer if you calculate everything correctly.